All right, we are going to take our next speed test, first speed test of the week. Speed test 19 on the top of page 9. And as you look at it, be like, hey, this looks familiar. You got a lot of memorized units. Now, there are a few metric units on here as well that you'll want to think through King Henry on. So how many places would the decimal move from one place to the next? So if you want to, right now, before we start, go ahead and put your King Henry died unexpectedly drinking chocolate milk across the top or across the bottom so it's available to you to use. You're going to have a minute and a half to write these in because there's really no math at all. Okay, the first speed test of the year that there's literally no math. It's just, do you remember all these? So here we go, minute and a half. Speed test 19, and you may begin. People already done? All right, stop. Pencils down. Sound mix it up today. Different sound effect. Yeah. All right, exchange the person behind you, person in the back. Bring yours to the front.
Versus back.
Exchange with the person behind you. If you're at the back, there's no one behind you, so bring it to the front. In pen. Pencils now off your desks. In pen, sign your name as the grader. In pen, sign your name as the grader. And these are going to be 5 points each. What I'm going to do is I'm going to go down each column, okay? And at the bottom of each column, we'll put the total number wrong. Sound good? So tracking with me here, we're going to go down the first column, number 1, then 5, 9, 13, 17. Your answers. 1 quart equals 2 pints, 2. A meter's 100 centimeters, 100. A bushel is 4 pecks, 4. A decade is 10 years, 10. And a meter is 1,000 millimeters, 1,000. At the bottom of the first column, put the total number wrong. Let's go down the next column, beginning with number 2. Your answers are 3, 8, 100, 2,000, 2. Total number wrong at the bottom of that column. The third column, beginning with number 3. Your answers are 5,280, 365, 10, 3, 1,000. Total number wrong at the bottom of that column. Again, hopefully these are minus zeros. And the final column, your answers are 36, 16, 8, 1,760, 7. All right, figure the total number wrong, multiply by 5. That's how many points off. So then subtract that from 100. So 5 points each. Figure the score to the best of your ability. Put it in the score blank. Also, don't forget to put it on the score page where it says Speed Drill 19. Speed Drill 19. Put it on that score page. Remember, all of these, there's 13 this quarter. All 13 of them will get averaged together to be 1 quiz grade this year. This quarter. All right, print fill at the front. Take them to the back. Everybody else just pass them to the person in front of you. And I am curious if we had any hundreds. Any hundreds? A few. How about 95? So you only missed one thing. How about 90s? Only missed two things. Still got an A. Really solid. How about B's? You missed 3 or 4. Made an 80 something. 80 or 85? Questions at all? I don't know there should be, but are there any questions? Yes, sir?
It's not really a necessary question, but how much points would you take off if we did it in pencil?
You're supposed to do it in pencil.
I mean in pen.
Oh, in pen, 3 points for not following directions. All right, pass those forward if you would, please. Take the books out. Turn to page 144. Pass them forward and take the books out. Page 144. We began a section yesterday. Earth measurement. What is that word that means to measure the earth, Sam? Geometry. So we began a section on geometry yesterday and talked about several different geometric concepts, geometric figures. And we said most of what we focus on in this early section of geometry is going to involve figures that you could draw on a flat surface. What's the name for any flat surface, Luciana?
Plane.
A plane. And what do we call any figure that can be drawn on a plane, Michael? A plane figure. Mathematicians aren't particularly creative. You're turning to page 144 right now, being ready there. On page 144, we're going to get to that in a moment. We talked about a mathematician, a Greek guy, many, many thousands of years ago, and who wrote a 13-volume collection that laid the foundations for geometry. Who was the guy, first of all? Euclid. You read well. And what was the book that he... People would be like, how'd she remember that? Cheater. All right, and Euclid wrote what 13-volume work?
The Elements.
The Elements. Did you look that up too?
I went back and
Just went back and looked. All right, so what was the guy's name, class, without looking?
Euclid.
And he wrote a 13-volume work called The Elements. There we go. And with geometry, we talked about several different plane figures. The most basic of all plane figures is just some exact location in space. Maybe that one right there. Well, technically, this exact location in space is of infinite smallness, right? But we have to represent it some way, and we can't see infinite smallness, so we simply use a dot to represent class a point. How do we name a point? If we wanted to name this point, we wouldn't name it Bob or George or anything like that. We might name it how, Kirsten?
Point A.
Okay, with a capital letter. We could use A if we really liked A. We could use K. We could use B. We could use S. We could use whatever, right? Just a capital letter to notate a point. Well, if I were to pick some other point, some other exact location in space, maybe we call this point B. We understand that if I were to take my, my handy-dandy meter stick here, how many lines, class, could I draw through A? How many lines could I draw through A? Infinite number, right? How many lines could I draw through B?
Infinite.
How many lines could I draw through A and B?
One.
Only one line that would go through both A
Drop
and
from
B. Let's try that again. Hey, I don't laugh at you when you strike out, okay?
You can't
I am
do one,
vicious,
too.
vicious, I know. Mean guy. And this line technically goes off class to infinity in both directions, doesn't it? Just keeps going and going and going. What if, though, I only wanted this portion of the line between A and B? This isn't the whole line, class. This would be called just a line segment. Very good. Again, we'd name it based on these 2 points. We would name a line segment AB by simply putting this over the top. But if we wanted to refer to the entire line of infinite length, class, we would put arrows on the ends to show that we refer to the whole line AB. What if, though, I didn't really want a whole line? I only wanted to start at A and then go through B. What figure would this be now, Corey? Array. And to notate that, I just wouldn't have an arrow on the end of A, I'd just have an arrow on the end of B. If it had gone the other way, then I would have called it BA, and I would have had the dot at B and have the arrow going through A. Right? We just name it however we need to indicate where the end is. I could also draw some line, and instead of using 2 points to name the line, or even a line segment for that matter, I could use a single letter. But if I use just one letter, Bryson, I need to have it be the other one. Class? Lowercase.
Oh.
I could just call this L, for instance. Well, this would simply be line L. We wouldn't use the notation over a single lowercase letter. I could draw another line. And we could call this line M. And we could say that line L and line M are what type of lines, class? Intersecting lines. And most lines will intersect at some point. In fact, it's special if they don't. If somehow I had drawn line M, or let's go with another line instead. Let's call this line N. If somehow I draw line N so that it doesn't intersect. Now on the surface though, I don't know, maybe it's my perspective. Do you think if I extended them far enough, do you think eventually they'd intersect?
Yeah.
I don't know that they look quite perfect. I try to draw them perfect. Let's just assume I'm perfect here and could draw this, or let's at least assume I could draw perfectly. If these lines, no matter how far you extend them, would never intersect, we would describe these lines, Elaine, as being
Parallel.
Now, what's the notation for parallel, Jalen? Do you remember?
So line NL, like an 11.
Good. It looks like an 11. Line N is parallel to line L. And that's how we would notate parallel. It's also possible, let me come over here with this AB line, that I could not just draw a line that intersects, right? So we could name this line CG. And this line CG, it's possible I could draw, so it doesn't just intersect, but it actually intersects to make a 90-degree angle. What do we call a 90-degree angle, class?
Right
A right angle. What would we call lines that make right angles in all four spots? We use these little boxes to show that they're right angles, but what do we call those lines? Michael? Perpendicular lines. Now, perpendicular is a really long word. Mathematicians are lazy. So mathematicians have a way of saying that line AB and line CG are perpendicular. What was that symbol, Kirsten? The upside down T. And that shows that the lines are perpendicular with each other. These were the first several things we talked through, and this is what the first portion of the homework was over. Page 144, you did just numbers 1 through 8 on this page. You did what page? Oh, there it is. There, that looks like 1 through 8. No, that's this 1 through 17, not the 1 through 8 also. Okay. There's the 1 through 8. I'm going to check the next page of homework in just a moment. For now, just looking for the 1 through 8. We didn't actually talk about that yet, so that's why I didn't assign it. But you're more than happy to try it if you want. All right. So number 1, what is the meaning of that symbol, Ben?
It's a ray.
Specifically, which ray? What's the name of the ray?
EV.
Ray EV. There we go. Number 2, what does all that notation mean? I'm losing track of where I was going with that. Jalen.
Line FG is perpendicular to line LM.
Good. Line FG is perpendicular line LM. Well, number 3. This is one of the things I forgot. I felt like I was forgetting something. Bryson, what does that notation mean? Angle RST, which means we've got either a couple of line segments or a couple of rays. I'm going to go with line segments for a change because we usually use rays. But RST. I know that S, the middle letter, has to be the point where these two line segments, or they could be rays, come together. Class, what do we call the point where the two segments or rays meet? It's called the vertex of the angle. What do we call RS and ST, these two rays or line segments, class?
Sides.
These are called the sides of the angle. So we have two sides to an angle and a vertex. What would be another way to name this same angle, Luciana? We could just call it angle S, because there's only one angle at S, and we could also name it, class, angle TSR. Number 4, how would we notate that figure, Michael?
X, Y, with the line over it with arrows, then and the 11, with the percent.
Strange sound out the window. Okay, keep going.
And then QB with the line over it.
Good. How many have this as your notation for number 4? Number 5, how would we notate that? Kirsten.
With like the, I don't
The
know.
angle symbol is what it's called, just the angle symbol.
When an X, Y, Z,
Or
or Z, Y, X,
angle ZYX, or
or angle X, or
we wouldn't call it X,
well, angle Y.
angle Y, because we name it by the vertex. Good. And then what about number 6, Ben?
6.
What is that?
AC,
Right, it's AC, but it's a what? It's a
line segment.
line segment. How do we notate that AC is a line segment?
Put a line over it.
Put a line over without the arrowheads on it. Number 7, what kind of lines intersect to form 4 right angles, class? Perpendicular lines. And what is a portion of a line having 2 endpoints, class?
Line segment.
Line segment. Flip over to page 147. Page 147. And you were supposed to draw and label pictures of each of these different figures. And so for a line, all you had to do was draw some straight line with arrows on the ends, and you could name either with 2 capital letters or with 1 lowercase letter. For number 2, you should have drawn some angle. Now, by the way, we usually draw angles little. I mean, you can draw it big like this, right? It doesn't have to be necessarily small, right? But again, you could either name it with a single letter here, or you could pick a couple of letters here and name it with 3 letters. For array, just as long as it starts at 1 point and goes to infinity in some direction, doesn't really matter which direction it goes, you'll name the point, you'll name another point along the ray. Line segment, just make sure you have 2 endpoints, each labeled with capital letters. For a rectangle, what should a rectangle look like, Sam?
Two parallel lines, but different from the other two.
You're not wrong, but there's an important detail you're not including on rectangle. Elaine?
So it should be like a long, like, pulled out box, and it should have 4 right angles.
There we go. You're right, Sam. We will have 2 parallel lines here and 2 parallel lines here, where generally we assume that 2 of the lines are longer than the other 2, but the key is they've got to have right angles in all 4 corners. That's what makes it a rectangle. What if, class, all we had were a couple of parallel lines here and a couple of parallel lines here? Then is it necessarily a rectangle, class?
No.
No, what would we call this figure, anyone?
Parallelogram.
Parallelogram. So if it's got the parallel lines, it's a parallelogram. It's not until you put right angles that makes it a rectangle. What about a trapezoid? Corey, what should we draw for a trapezoid?
A line, then like a short line at the top, and then a line diagonal.
Diagonal.
It's a little bit diagonal. What's the key, class? How should I draw the next line? Anyone? Parallel to this one. That's the key. You've got to have 2 lines that are parallel and 2 lines that aren't parallel. So check your drawing on number 6. You have 2 lines that are parallel. Now, it could even be like this. A line here and a line here. Those are parallel. Those 2 aren't parallel. That would still be a trapezoid as long as 2 lines are parallel. Does that make sense? Let's see. Parallel lines, obviously. Parallel lines. And intersecting lines. Draw some intersecting lines. On these figures, let's just go with the trapezoid. It did say to label a picture with this trapezoid. How should I name each of these corners, class?
Letters.
What kind of letters?
Oh.
Capital letters. So we could go, W, X, Y, Z. What do we call the points where these lines or line segments come together, class?
Vertex.
Vertices. Each one is a vertex, but the plural, since there's 4 of them, vertices. What do we call the lines or line segments, rather, that make up the figure? Sides. Number 9. What do we call a parallelogram that has 4 right angles, class? D, a rectangle. D for number 9. Number 10 is? H. A triangle is our 3-sided polygon. Number 11. E, a parallelogram with all sides equal. Come over to your parallelogram. Let's see how these top sides are short or longer. Well, what if we shorten them up? And all 4 sides are now equal. Well, it's still a parallelogram, but it has a special name now, class.
Rhombus.
We call it a rhombus. So that would be letter
B.
B, oh, excuse me, E. Sorry, we're on number 11. E is the wrong, sorry. Number 12, quadrilateral whose opposite sides are parallel. That's B, the parallelogram. That's what we had a moment ago up there. Number 13, a quadrilateral having only one pair of opposite sides parallel. G, that's the trapezoid. And then an 8-sided polygon. A, that's the octagon. Number 15, 16, 17, just some basic fraction review. But number 15 class, we're trying to add fractions. And in order to add fractions, you gotta have a
Common denominator.
What is the common denominator on number 15, Luciana? 12. We need to get 12ths for our denominator. What was your answer to number 15? 18 and 5/12 is correct. Number 16, we're multiplying. Do we need a common denominator to multiply, class?
No.
No. Sam, what should we do, though, before we start multiplying stuff? There's a shortcut.
I like simplifying fractions.
Yeah, how do we simplify it? What do we call that? Anyone?
Cancel.
Canceling. Yeah, what can we cancel on number 16, Sam? 5 and 20 to get? 4 and 1. What else? 18 and 9 to get? 2 and 1, which when you multiply gives you? Oh my. Okay, Sam. You had an 18/20 times 5/9, and you said cancel to get a 1 and 4, and you said cancel to get a 1 and a 2. No, you're right. So Sam, if you multiply, look at it this way. All you have is a 2 times 1. And all you got in the bottom is a 4 times 1. 4. Does that make sense?
Yeah.
But we're still not done. Anyone?
Cancel.
1/2. And you could have actually canceled here to get the 1/2, or you could reduce your 2/4 to get 1/2. Number 17. What is that thing, Elaine?
Complex fraction.
Complex fraction. And a complex fraction really is just what, class?
Multiplication.
It's a division problem, right? It's really a division problem. That's what the fraction bar means. But we really don't even divide. We
Multiply
by the reciprocal. So we're going to write this problem number 17 as a multiplication problem by the time it's all said and done. What's it going to look like, Kirsten?
49/12 times 29/7.
That's a 24/7, so that's going to affect your answer there. We can cancel some stuff here, Kirsten.
The 12 and the 24 to get 2 and 1.
All right.
And the 7 and the 49 to get 1 and 7.
So when we multiply, what's our answer?
14.
14. Technically over 1, but we're too lazy to write the over 1, so just 14 our answer. How many perfect? 15, 16, 17? Questions on fractions? Yes, sir. Any questions on this? Any questions on the homework at all?
In every single polygon, is there going to be an angle?
Well, there has to be at least 3 angles because the smallest polygon has 3 sides. Remember we said if you have only one side, you have a line segment. If you have 2 sides, you have an angle. If you have 3 sides, now you can form a triangle. And a triangle, tri meaning 3, has 1, 2, 3 different angles in it. So a polygon always has at least 3 angles. Good question. Look across the page 146. A couple things we did not have time to get to yesterday. Time kind of ran out on us. I want you to note these terms. Notice that first sentence at the top of page 146. Polygons that are the exact same shape and size are congruent to each other. Say that word with me, class. Congruent. Again, say that word.
Congruent.
Congruent means they are exactly the same. Every last little detail exactly the same. Is there something in the room we could look at and say, oh, those things are congruent to each other? Yes? Well, not exactly the same because, the printing on them is different, but we would say the shape of the flag and all of that. The dimensions are all the same, sure.
They're erasers?
Most of them. Now, this one's not, but the other erasers are roughly congruent to each other, we might say. Elaine?
Speed drill books.
All the speed drill, well, the written content, no, but the dimensions are all exactly the same. Ben?
4
Well, what would it be congruent to?
to other floor.
No.
Like the tiles.
Oh, all the ceiling tiles are a little congruent. Now, I think there might be some here that got trimmed a little short, but most of the ceiling tiles are congruent with each other. Right, the desks would be congruent to you, exactly the same. And we show congruency with this symbol. I want you to circle it or mark it. It's an equal sign with a squiggle on top. Not, by the way, I saw this on a recent quiz or test, not a squiggle like that. Okay, not one of these kind of squiggles, just a single up, down, up squiggle. This is the symbol for congruent. If two things are exactly the same. Now, it's possible to have two things that aren't quite exactly the same, but they're the same shape at least. For instance, squares. I could have a big square, I could have a little square. But everyone can look right at it and say, those are identical, almost, squares. They're the same shape at least, right? Stop signs. You have the actual stop sign, and then how many have ever, I don't know, done the stop and let me tell you song? You've seen like a little mini stop sign. Okay, stop signs are all the same shape. They're not always the same size, though the official ones are, but stop signs are all the same shape. They're not quite the same size. That term is the term similar. Mark that sentence of the next paragraph. When polygons are the exact same shape, but not the exact same size, they are similar to each other. That symbol is the squiggle without the equal sign. So we've seen the squiggle before. Remember we saw this squiggle, double squiggle? Squiggly equal sign meant approximately equal to. If you put a squiggle with an equal sign, class, that means congruent. And just a single squiggle means similar. What does a single squiggle mean, class? Similar. And similar polygons or similar figures are figures that have the same shape, but not quite the same size. There we go. Let's go and drill through some things. Put your pencil in your book, close your book, and let's drill through some of these different geometric concepts here. Class, an exact location in space is called a point. This would be a line. This here would be a line segment. Ray. This here would be an angle. Specifically, we'd name it angle XYZ, or just angle Y would be the easy way to say it. These lines are intersecting lines, but these lines more specifically are perpendicular. These lines would be parallel to each other. We said that any figure that starts and eventually ends at the same point, class, can be called a closed figure. But if the closed figure is made of only straight lines, Jalen, we call it a polygon. And all of these figures here are bounded by only straight lines. These would be all polygons. This polygon has parallel sides everywhere. Parallelogram. This is a parallelogram, isn't it? But we have a special name because it has right angles. So we call it a rectangle. This is a rectangle. But the sides are all the same. So we call it a square. By the way, are all rectangles similar? No. Because you could have a really short, squatty rectangle, and you could have a rectangle like this. Now, they're both rectangles, aren't they? But are they the same shape? No. What if I drew a rectangle that looked like, and I'm trying for it, this? Do those look like they're the same shape?
No.
I tried to make them the same shape. They're pretty close. They're definitely not the same size, but they're pretty much the same shape. These two wouldn't be even remotely close. These ones are pretty close. Could two rectangles be similar? Could two rectangles be congruent? Yeah, if I drew another rectangle like this one here, we could have congruent, that's a big equal sign. We could have two congruent rectangles, so can rectangles be congruent? Yes. Can they be similar? Can they be not similar? Could squares ever be congruent? Absolutely. Could squares ever be similar? Could squares ever be not similar? No. Squares are always at least similar to each other, right? A one square is always the exact same shape as another square, right? Always the exact same shape. A rectangle gives you a little more freedom to change the dimensions, to stretch it, squish it, whatever. A square has to be uniform throughout, so squares will always at least be similar. Question, Jalen?
The one in the middle.
There's not one in the middle, that's just empty space.
No,
This one.
yeah, that's more of a trapezoid. It's got a diagonal line.
Well, it's supposed to be a rectangle, smart Alec. All right, I'm no artist up here, okay? I'm not using computer-generated graphics. All right, back to the parallelogram. But if the sides of the parallelogram, Ben, facing the front, if the sides are all the same, we call it a
Rhombus.
rhombus. Here we have a
Trapezoid.
because how many sides are parallel?
Two.
Only two. One pair of sides, or you could say two sides are parallel, but there are two non-parallel sides. By the way, if you were to have a perpendicular side, it'd be called a right trapezoid. This one's not a right trapezoid. Both sides are a little bit slanty. If we have 5 sides,
Pentagon.
what is it called?
Airplane.
Pentagon. 5 sides is called class A
Pentagon.
pentagon, because penta refers to 5. I'm not sure how you can remember that. Here we have a
Stop sign.
no, careful. This is not a stop sign. It's got 6 sides to it. Hexagon. You can remember this. 6 has the X in it, and hexagon has the X in it as well. So maybe remember sixagon, hexagon, whatever. Now this one wasn't actually in your book. I'm not quite sure why it's included with the flashcards, but I'll ask it anyway. This is a weird one. It's got 7 sides. Heptagon. Someone remember from a past year what it's called? The heptagon with the 7 sides. You can tell because it kind of looks wonky, right? Nothing's quite symmetric. Here's your stop sign.
Stop sign.
And that's an octagon. It's also the UFC. Anyway, these 2 triangles are exactly the same. They're congruent. These 2 triangles aren't exactly the same. One's littler than the other.
Similar.
These would be similar polygons. Let's run through these real quick. Mix it up. We'll do a review game tomorrow. We don't have a lot of time for it now, but we will tomorrow. Mix it up here. Let's go row on row. Michael doesn't have his glasses, so everybody else has an unfair advantage over Michael. All right, so let's start with Michael's row. Pentagon, Jalen.
Airplane.
Line segment.
Line segment, very good. Ray, Corey. Rectangle is one of the middle 2 there. I'm not quite sure which one I heard.
Square.
That was a tie in the back.
Rhombus.
Rhombus, Corey again.
Go.
Similar.
Similar.
Octagon.
Octagon, yes.
Stop sign. Heptagon.
Heptagon is the weird one. Good job. The 7-sided one.
Similar. Congruent.
Congruent. They are congruent. Exactly the same.
Angle.
It's just an angle. Good. 2 rays there pictured. Yes.
Will a heptagon be on the test?
I don't think so.
Polygons.
Just polygons. They're closed figures, but they're all bounded by straight lines. Those are just polygons, an assortment there.
Parallelogram.
Parallelogram. Yes, parallelogram.
I was like, what were we looking at?
Point.
I said dot.
Hexagon.
Hexagon. Hexagon. 6 sides. Yeah, not a dot. I put point on that earlier one there, Kirsten.
Right. Line.
That's a line.
Right. Line. Intersecting lines.
Intersecting lines. Good, Kirsten. Got that word out quick. That was a long word.
Perpendicular lines.
Also got a word out quick. Perpendicular lines. The fast mouth in the back. Good job, Griffin. Parallel lines. I think that was a 3-way tie.
Trapezoid.
Trapezoid. Good, Kirsten. Pentagon. 5 sides
I
there.
recognize every
Pentagon.
Yes. All right. Flip back in your notes if you would, please, or flip ahead in your books if you would, please, to page 148. Page 148. I need you to mark the first sentence on the page, the term perimeter. And most of you will remember this term from your elementary days as well. Perimeter refers to the distance around a polygon. Perimeter refers to the distance around a polygon. If we were looking at this classroom and we had to put this brown base molding all the way around, it's kind of nasty looking, it's old, we want new base molding, that'd be great. And so we rip it all up and we need to put down more. Well, I need to know the distance around the room so I can get the base molding, minus, of course, the door, because we don't need to put base molding there. But I need to know the distance around. That would be perimeter. On Wednesday, when you run, you're going to be running the perimeter of the field for 12 minutes, right? Perimeter, distance around. See, math connection. Now, how would we find the perimeter of a polygon? Well, just add up all the sides together and it gives you the perimeter. Does that make sense? So if you would mark this, it's the sum of the sides. Write that off to the side margin. It's the sum of the sides. It's simply the sum of the sides. or all the sides added together, but it's faster to say the sum of the sides. Look at the example problem. They give us a goofy looking pentagon. And notice the lengths of the sides. 2.1 centimeters, 4.3 centimeters, 3.5 centimeters, 2 centimeters, 3 centimeters. You know what they had to do to find the perimeter, class?
Measure.
Add them all together. And so they added them all together, and they got 14.9 centimeters. Seem pretty easy? Now, there are some shortcuts you can use, Jalen. Peace be still. There are some shortcuts you can use. For instance, with a rectangle, you know that the two sides that are vertical are going to be the same length. And you know the two sides that are horizontal are also going to be the same length. We refer in a triangle usually to the shorter sides as the width of the rectangle. And there's two of them, right? And we refer to the longer sides as the lengths of the rectangle. Well, rather than adding up all of that, since there's two of these lengths, we could just say 2 times the length plus, and we could just say 2 times the width. How many remember this formula for the perimeter of a rectangle? P equals 2 times L plus 2 times W. You say, what if I don't remember that? Well, that's a bummer, but you could, of course, just add them all 4 together. It's just faster to do it this way. The same would actually be true if you were to take a parallelogram, though we don't use the term length and width necessarily, but these two sides have to be equal, and these two sides also have to be equal. So again, you could multiply one of the sides. For instance, if this was 3 inches, class, we could multiply that by 2. 6 inches, keep that number in your head. We could say this is 10 inches, multiply that by 2,
20.
and add the 20 and the 6 together to get 26 inches. We don't necessarily have to add up all 4 sides. We can simply double sides that match. The square gives you even more possibilities, because what do I know about all 4 sides of a square, class?
Equal.
They're all 4 of them equal. So if I just know, for instance, that this is 5 inches, rather than adding 5 plus 5 plus 5 plus 5, the faster way to find this perimeter, class, would be to simply multiply by 4. 4 times the length of whatever side that I know. So we can say P equals 4S could be used to find the perimeter of a square. How many remember that formula from your elementary days? By the way, you could also use this formula for what other polygon?
Rhombus.
A rhombus could also be used there, right? Because we also know that all 4 sides of a rhombus are equal as well. It's a horrible rhombus, stop judging. And but we just multiply whatever the length of one side is by 4. So if I knew that this was 7 centimeters, class, what would be the perimeter of the rhombus? 28 centimeters. It's an easy way to find it. Technically, you could do this for any figure in which all the sides are equal. The book even points out in purple there a little hexagon. Well, if all the sides of the hexagon are the same, just multiply by 6 rather than adding them all together. And you see on table C, there at the bottom of page 148, put a star next to this, you've got a couple formulas you need to know. The rectangle, say it with me, class. P equals 2L plus 2W. Again, P equals 2L plus 2W. And we do understand, right, that when you put a 2 up against the L, or a 2 up against the W, that implies multiplication. I think we addressed things being pushed up against each other when we talked about order of operations. Square, class, say the formula with me. P equals 4S. Once again, the square is?
P equals 4S.
But for general sake, most polygons, class, all we got to do is find the sum of the sides. Question, Elaine.
Like you said, the 2 and the L is multiplication. Like, I always wrote it out like P equals 2
times L plus 2 times W. We were lazy.
Yeah.
So as you get older, we find ways to make it lazier. So rather than writing it out as 2 times L plus 2 times W, lazy mathematicians be like, hey, now that we know we just smush them, we're going to say 2L plus 2W.
Would you take off points on this?
I wouldn't take off points, but I'd probably write next to it, be lazy. And then I'd be mad because you made me write be lazy, and I was too lazy to want to write that in the first place. So then you get on my bad side and lose brownie points. See? So don't do that. Write it that way, because I'll be lazy. Now, remember this. Notice the use of tick marks here, right? What if I had a goofy-looking polygon? Something like that. And I marked that these two things were the same. I might not, maybe I marked that as the same thing as well. Maybe I say that this is 3 inches, I say that this is 7 inches, and I say that this is 11 inches. Does it seem like there's 2 sides I haven't marked, class? But I have, haven't I? By putting a tick mark on these 2 sides, I've told you, class, these sides are 7 inches. What would be the fast way to take care of all 3 of these sides? 3 times 7 is 21. And then I still have a 3 and an 11, class, which is an additional 14. Add that together to get 35. And we want to make sure to include the unit Inches. So this is one thing that you'll see on perimeter problems is they won't label every single side. If there's sides that are equal, they'll just mark them with tick marks. It's possible to have, for instance, in the first problem on page 149, notice they've got a couple of different sides marked with 2 tick marks. They've got a couple sides marked with 3 tick marks. They got a couple sides marked with 1 tick mark. Looking on page 149, Sam, the first problem on the page, that tells you how big the various sides are. At your seats, I want you to do 1 through 6. Find the perimeters of these different polygons. Yes, ma'am.
Did you say to do?
1 through 6. Yep. Sam, you did the second page of homework, right? It was just the first page. Which is page 144. Did you do it with me while we were doing this now?
I did. I did the first.
Okay, I'll check it tomorrow. Just make a note of it to make sure you get that done. 1 through 6, then pencil down, look this way so I know that you're finished. Michael's already finished. Bryson's finished. Good, Corey. Sam, Elaine. Head up there, Jalen. Probably stay awake. All right, pencils down. Let's take a look at these together. Number 1, Michael, you were first. What did you get for that perimeter?
56 meters.
Excellent job, 56 meters. I'd say, well, there's 2 14s, there's 2 6s, and 2 8s. 2 14s is 28, 2 6s is 12, 2 8s is 16. Add those 3 numbers together. That is a very weird looking hexagon, isn't it? It has 6 sides. It is a hexagon. It looks like a what? Kind of does look like a V, or if you flip it over, it looks like a tent. Number 2, what do we get for the perimeter of that triangle? Kirsten? 16 meters, and we call that an isosceles triangle. We're going to be looking at that in the next couple lessons. Number 3, we got another kind of looks like a tent. Funny looking pentagon here. Bryson?
43.
Ooh, careful, not 43 centimeters. So we've got a little addition error there.
No. 8.
Corey? 53 centimeters. 53 centimeters. I think we had a issue there in the column of the tens digit. Let me come back to you, Bryson, for redemption. Number 4, what did you get for the perimeter?
34 feet.
34 feet is correct. Number 5, how many sides we got there, class? 8. So that's an octagon. Okay, what's the perimeter going to be, Ben?
16 meters.
16 meters, there we go. Number 6, that appears to be a trapezoid. In fact, it appears to be what we call an isosceles trapezoid. What'd you get for the perimeter there, though? Sam?
11.5 yards.
11.5 yards is correct. How many got all the ones you did correct? All the ones you did were right. Do we need to see any of these worked out? Any other say, can you please show me this one? Yes, ma'am. No, the very first one. So, Luciano, you see we've got a side of 14 with a tick mark, and we've got another side with another tick mark. That means if this is 14, this is also 14. Then we've got a side here with 2 tick marks that's marked as 8. There's another side with 2 tick marks. That must also be 8. My artwork's not nearly as good as theirs. Then we've got a side with 3 tick marks that's 6. And we've got another side with 3 tick marks. That must also be 6. Does that make sense? So without necessarily labeling these other numbers, I'm like, well, there's 2 6s, 2 8s, and 2 14s. So double that, double that, and then add them all together. And that's where we get the 56 meters from. Does that make sense? All right, any others we need to see worked? Flip the page. What's the formula for the perimeter of a rectangle, class? P equals 2L plus 2W. What about the square? P equals 4S. All right, I've got a couple rectangles and I've got a square on there. Find the perimeters for numbers 7 through 9. Just numbers 7, 8, and 9 at the top of page 150.
Have they already multiplied it by 2 or not?
Why would they? Yes. All right, number 7, class. They ask for us to find the perimeter of a rectangle. So we're going to use the formula P equals 2L plus 2W. L stands, class, for length. And it tells us the length of the rectangle is 8.3 yards. Plus 2 times the W. W stands for, class, width. And they tell us the width is 6.9 yards. What is 2 times 8.3, anyone? Looking at your work. 16.6. And what's 2 times 6.9?
13.8.
Good, you just multiply by 2, and then we add, keeping in mind that we need to keep the decimal point lined up as we add, and we add, and we get 30, keep that decimal lined up, remember, not 2 decimal places, that's multiplication, just adding, and don't forget the yards. How many had 30.4 yards for number 7? Number 8, class, the formula for a square is just P equals 4S, which means we multiply their side by 4. Class, we get 36 inches. Number 9, notice how they describe the rectangle. They say it's a 24-foot by 32-foot rectangle. That's the length and the width. Which one's technically the length, though, class? The 32. The longer one is considered to be the length. The shorter one is considered to be the width, so the shorter one is 24. Here's the nice thing. It doesn't matter if you got it mixed up, as long as you double each of them. Double the 32, class.
64.
Double the 24. And then be sure to add those 2 doubled lengths and widths together to get 112. And this was feet, so 112 feet. How many had that answer for number 9? Any questions on how to use the formulas to find perimeter? Yes, sir. On number 8? So we plug into the formula P equals 4S. S stands for what, class? Side. So 4, and the side it says is 9 inches. 4 times 9 is 36 inches. That's all. Just multiply by 4. All right, your homework for this evening is to do page 150 to 151. Page 150 to 151 in the homework section 1 through 15. The homework section 1 through 15. Yep. Page 150 to 151, homework section, numbers 1 through 15. take a look at all of this in our next lesson when the bell rings. You'll be dismissed. Have a wonderful rest of your day.
We did it.